All right, so let's today look at section 12.7, which is tangent planes and linear approximations, which really are the same thing. There's really only one idea here. The rest is just notation and language and words and ways that something might be asked. And our goal here is the following. If I have a surface, if I have the graph of some surface, and I would like to know, the goal is to say, take it at any particular point. What we'd like to do is say, well, there's no tangent line, but there is a plane that is tangent to the surface. Right? So we know that we have equations of planes. Recall that a plane's something like 2x plus 3y minus z is 6. This is an equation of a plane where we have as linear as possible with all three variables, or x plus 3y minus 2z is 8. Right? These are both planes. Also recall that for this particular plane, I have a normal vector, which is 1, 3, minus 2. That's the vector that I pull off the coefficients of x, y, and z, and that's a vector that's normal to a plane. So if I want an equation of a plane, I need a point on the plane, and I need a vector that's normal to the plane. And if I have both of those things, then I can come up with the equation of the plane. So we're going to use those two ideas to find the equation of a tangent plane for any given surface. All right, so here's our idea. There's really one big idea here. Suppose that I have the function f at x, y, z. Let's just start with our favorite, x squared plus y squared, the paraboloid. And I think about this as x squared plus z equals x squared plus y squared, and I put the z over onto the right. All right, so now I've got an equation, but it's more, I haven't solved for z, that's fine. I put all of the variables on the right-hand side, and I've got 0 over here. Let's look at the function of 3 variables. Big F at x, y, z is x squared plus y squared minus z. This curve, or function, this surface, I get the equation by setting 0 in for f. So little f is a level surface for big F. Because if I take the equation for big F and I put a constant in, that is 0, if I put the constant 0 in, then I get the equation of little f back. Well, we know from our previous discussion that gradient vectors are perpendicular to level curves and therefore also to level surfaces. So this tells me that the gradient vector of big F at a particular point is perpendicular to the surface little f at x, y. So let's put that into action. Let's calculate the gradient vector of big F. All right, so big F is just the equation that we started with, the function that we started with, but we moved z to the other side. And then the gradient is the partial derivatives, which in this case is 2x. Everything else goes to 0. For the derivative with respect to y, I get 2y. Everything else goes to 0. And the derivative with respect to z is -1. So this is my gradient vector for this function of 3 variables. That's really f at x, y, and z. All right, so let's use this to find the tangent plane to little f at the point 1, 1. All right, so we're at the point 1, 1. Well, if we're at the point 1, 1, and we're on our paraboloid, 1, 1. But we also need to know what the z value is. So z is f at 1, 1, which is 1 squared plus 1 squared, which is 2. So really we're at the point 1, 1, 2. And we're going to use that to calculate grad f. Grad big F at this point is 2, 2, negative 1. But our previous idea says that the gradient vector is normal to a level surface, but this is a level surface. This is our level surface, so we can use this as the normal vector to the surface at that particular point. But the normal vector to the surface is the same thing as the normal vector to our tangent plane. So our normal vector is 2, 2 minus 1. Which was grad big F at 1, 1, 2. Now I have a point, 1, 1, 2, and I have a normal vector, 2, 2 minus 1, and I can use those to write down the equation of a plane. So 2x component plus 2y, the y goes with y, minus z, minus 1 goes here, and then this has to equal something, which I can use my point to figure out what the constant on the right is. 2 times 1 plus 2 times 1 minus 2 has got to be d. Well, that's 2. So the tangent plane is 2x plus 2y minus z is 2. So let's take a second to look at Mathematica. We'll graph this function. We'll graph this tangent plane at the same time, and we'll see that it actually works.
And so now we'll look at a Mathematica plot of our function y equals x squared, or z equals x squared plus y squared, along with its tangent plane that we just calculated. Notice the syntax. The two functions that we're calculating are in braces. Both have been solved for z. So the first is z equals x squared plus y squared, and the second is z equals 2x plus 2y minus 2, which is the tangent plane that we calculated, solved for z. The next two commands just tell it to plot between negative 5 and 5 for both x and y. Shift enter to evaluate. We look at our plots, and if we move things around, we notice that this really does appear to be the tangent plane at the point in question. So our method of using the gradient vector, that is f sub x and f sub y, to calculate the equation for a tangent plane certainly appears to have worked.
All right, let's look at another example. Suppose that we had the function, suppose that we had a surface. All right, so rather than just a function f at x, y, z, suppose that we actually had a surface. Let's look at maybe one of our hyperboloids. So how about x squared plus y squared minus z squared is equal to 1. This was, remember, our hyperboloid, something that does this sort of deal, moving up and down. Right, so let's find the tangent plane at the point. If I put in the point 1, 0, 1, it satisfies the equation. So I have a point which satisfies the equation, and I can ask for its tangent plane. Actually, we'll need, let's say, 1, 1, 1, because I get 1 squared plus 1 squared minus 1 squared, that equals 1. So let's find the tangent plane at this particular point. We're going to do the same thing. We're going to treat this as a level surface of the function x squared plus y squared minus z squared minus 1. So I bring my 1 over to the left. Then I have it set equal to 0. So it is a level surface of this function. I calculate the gradient vector, which is 2x, 2y, minus 2z. and I evaluate it at this point. 2, 2, minus 2. That's the normal vector to the surface, so it's also the normal vector to the tangent plane. 2, 2, minus 2. So now I've got a point, and I've got a normal vector, and I can do the same thing to come up with the tangent plane. 2x plus 2y, there's our 2 and the 2, minus 2z, that minus 2 is the coefficient of z, this is equal to some constant, and I evaluate that constant by using the point. And that's 2, 4 minus 2 is 2, so the answer is 2x plus 2y minus 2z is 2. Again, let's look at Mathematica, where we'll graph this surface and graph this tangent plane and see that they match.
And in this example, we are plotting the function x square root of x squared plus y squared minus 1. So remember, in the lecture, we actually looked at x squared plus y squared minus z squared equals 1. So I solved that for z and plotted that function, and also plotted the plane x plus y minus 1, which is the plane that we calculated, 2x plus 2y minus 2z equals 2, also solved for z. So I plotted both of those in our favorite beginning frame, minus 5 to 5. It's a little tough to be confident based on this picture that right at the point 1, 1, 1, it is the tangent plane. So I've zoomed in down in this second picture, just graphed it closer to the point 1, 1, 1, and this makes it pretty clear that in fact the tangent plane we calculated is the correct tangent plane at the point 1, 1, 1.
All right. Something just a little bit different, but not really. You may be asked to find a linear approximation to a function at a point. Really, that's just different words that says find the tangent plane and set it up as a function. So solve for z, essentially. So what we need to do is find the tangent plane, solve for z. So let's find the linear approximation to the function f of xy is e to the x squared y at the point minus 1, 2. So we're doing the same thing. There's really nothing different. We're going to find the tangent plane, and then we're going to solve for z. So first, we think about this as a function for which this is a level surface. And so this is z equals, and we solve, we put the z on the other side. E to the x squared y minus z, so big F of xy is z. We find its gradient vector. Grad f is, if I take the derivative with respect to x, e to the exponent times the derivative of the exponent with respect to x is 2xy. The derivative with respect to y, e to the x squared times y times the derivative with respect to y is x squared. And the derivative with respect to z is minus 1. Okay. Now I need to evaluate the gradient vector at this point, but be careful. I really need the point on the surface. So this is the point minus 1, 2, which becomes minus 1, 2, but we're also plugged that in to figure out what the z value is. And so that's e to the 2, e squared. So now, grad f at minus 1, 2, e squared. And we just see what we get. So this becomes e squared times negative 2, times negative 4. When I plug minus 1, 2 in, I get a negative 4 here, and then I get an e squared there. When I plug minus 1, 2 in for x and y, this is still e squared, and now it's just a positive 1, so e squared, and then minus 1. And that's the normal vector. So our point is minus 1, 2, e squared. Our normal vector is minus 4 e squared minus 1. And we just find the equation of that plane. If I find the equation of that plane, we find minus 4e squared x plus e squared y, that's just a number, constant, that's just a constant, minus z, and that's got to equal some constant d, which again we figured out by plugging the points in for x, y, z. So minus 4 e squared times minus 1 plus e squared times 2 minus e squared, that had better be d. Well, that's 4e squared plus 2e squared is 6e squared minus e squared is 5e squared is d. So the equation of this plane is minus 4 e squared x plus e squared y minus z is 5e squared. And finally, when we talk about a linear approximation, I need to solve for z. So I'm going to bring z over to the right and this over to the left. And I get z is equal to negative 4e squared x plus e squared y minus 5e squared. So we solve for z. And then when we talk about linear approximations, rather than writing z equals, we're going to write it as a function. L of xy for L for linear. And the idea here is if I think about this as a linear approximation, if I put an x, y that are close to the point that we started at, right? So we started at a point and found the tangent plane. If I put in a point that's close to that into this linear approximation, I get a value for the function which is approximately equal to the actual function value. But linear planes are much easier to algebraically work with than many complicated functions. And that's all we really need to say at this point about section 12.7. Next, we'll move into 12.8. All right, 12.8, optimization. Our real question at this point is to look at a function with some graph, and our goal is to find the point where this graph has its maximum value. So we're looking for these max or min values. Now in Calc 1, we knew how to do that. If I were looking for max or min values in Calc 1, I was looking for places where we had a horizontal tangent line. A horizontal tangent line, that is f prime equals 0, was a point where we had a maximum value or a minimum value. So a point with a horizontal tangent line was good. But we can see what we're looking for analogously here. Really what we're looking for is a point with, instead of a horizontal tangent line, we want a horizontal tangent plane. If we had a horizontal tangent plane, well then that's where we're going to get these local or relative maximum. We could have possibly a minimum value instead. Well, we already, just a few minutes ago, talked about tangent planes. So let's just recall a few things about that. So if I had a function f at xy to start with, we turn that into big F at xy, which was little f at xy minus z, so that we had a level surface. Turned this into a level surface for big F, and we looked at grad f of big F, which is, but if I take the gradient, if I take the gradient of big F, take the derivative with respect to x, notice that the z goes away. And so really all that I get is f sub x from the little f. If I take the gradient with respect, or the derivative with respect to y, I get f sub y, and then our z is always going to be minus 1 when I take the gradient of big F. Which means that my normal vector to my surface, and also then the normal vector for the tangent plane will be fx, fy minus 1. Which means when I go to write down the tangent plane, I'm going to get f sub x times x plus f sub y times y minus z is equal to some constant on the right. And I don't even care about what that constant on the right is. Right. And so if I solve for z, that is in a linear approximation, or if I just solve for z right from here, we get f sub x, x plus f sub y, y minus d. If I bring the z over and the d over as well. So this is what the tangent plane looks like, generically speaking, without any information about the function f and without any information about the point in question. When is a plane horizontal? Well, a plane is horizontal if it's just z equals some constant, if there are no x and y components. So it's horizontal if f sub x and f sub y are both 0. And so another way of saying that is if grad of little f is 0. So what I'm really looking for when I'm trying to find a maximum or a minimum value is I'm looking for a horizontal tangent plane, and that comes down to asking when is the gradient vector 0, which in other words is saying when are both partial derivatives equal to 0. So now rather than just looking for a point where the derivative is equal to 0, well, we got the next best thing. We've got two basic partial derivatives for functions of several variables, and we just need to look for points where both are 0. And so let's do that with a couple of examples. So let's look at a basic example of finding these maximum or minimum values, the place where we have horizontal tangent lines. So how about f of xy is x squared plus 2x plus y squared minus 4y. As it turns out, this is actually going to be very similar to a paraboloid, but it's just going to change the base point. It won't be at 0, 0 anymore. We could do that by completing the square, and it's actually not going to be a perfectly symmetric paraboloid. The cross sections aren't circles; they'll be ellipses instead. But that's okay. But we still get the same basic shape as our paraboloid. So what I'm looking for is points where f sub x is 0 and f sub y is 0. And we're going to call these things the same as in Calc 1. These are going to be critical points, points where the derivative is 0. In this case, the gradient vector, that is both partial derivatives. So f sub x is 2x plus 2, and f sub y is 2y minus 4. Well, if this is 0, then I get that x is minus 1. And if this is 0, I get that y is 2. So there's only one point that works, minus 2, 1. That's a critical point. That's the point where I'm going to have either the top, in this case of the paraboloid, or the bottom of the paraboloid. And in just a little bit, we'll talk about ways to classify whether it's a max or a min. Remember, there were several methods in Calc 1. The second derivative test was our favorite. We're going to come up with a version of the second derivative test for these functions of several variables as well. But for now, that's the single critical point. Let's take a look at its Mathematica graph just to confirm that it works the way we'd like.
And here we've plotted our latest function, z equals x squared plus 2x plus y squared minus 4y. I plotted it over a reasonably big range, negative 20 to 20 and negative 20 to 20 for x and y. I've also included our axes labels, x, y, and z, so we can be sure that we're comfortable with where we are. Now, remember that we calculated that the minimum value should be at negative 1, 2. Now, that's negative 1 for x and 2 for y. Also notice that this does appear like a paraboloid shape. If we expand it out further, we'd see an even better representation of a paraboloid shape. All right, so where does that minimum value actually occur? All right, so at what x value does that minimum value occur? If we look at it here, it's maybe not exactly clear. It does appear like it's a little bit to the left of 0. And if we look on the y value also appears actually to be a little bit to the right of 0. Let's zoom in a little bit because we wanted to see that it actually was around -1, 2. So let's say that x goes from -2 to 4, just to zoom in around x. And let's say that y goes from -2 to 4 as well. If we do this and we're looking for our minimum value, so now it's pretty clear that this y value is right at y equal 2. That's where our minimum y value occurs. If we spin it around to look at our x values, this minimum value occurs right at x equal -1 as well. So our picture confirms what we calculated with the math, and we're happy with what we found.
All right, so let's look at a bit more of a complicated example. Here's this function, f of xy is xy, e to the minus x minus y. Let's find all critical points. Well, we need f sub x and we need f sub y, the partial derivatives. Now this one's a bit more complicated because we actually need to apply the product rule. We have an x, and then we have an x in the exponent for e to the x. So we have to apply the product rule. I'm going to think about this as my product. If I apply the product rule, the first is xy, the derivative of the second is e to the exponent times the derivative of the exponent with respect to x, which is -1, plus the second, which is e to the minus x minus y, times the derivative of the first with respect to x. If x is the variable and y is the constant, the derivative is y. F sub y is going to be exactly analogous. We get xy e to the minus x minus y times -1 plus e to the minus x minus y now times x. Okay. So for this one, we're going to set it equal to 0, but we can actually factor some stuff out. We can factor out a y times e to the minus x minus y. And if we factor that out, what's left is a negative x, and what's left over here is a 1. And we have to set that equal to 0. For the second one, we can actually factor out an x and an e to the negative x minus y. And what's left is a negative y and a plus 1. So let's look at this for a second, because this one is a bit more confusing and more complicated than the simple one that we looked at just a minute ago. If I need both of these equations to be satisfied at the same time, that's the key point. I need both to be satisfied at the same time. If I just had that top equation, then I have a product of two things, actually three things, first, second, and then third, equals to 0. But if a product equals 0, then one of the terms must be 0. So this first equation is going to become y equals 0, e to the negative x minus y is 0, or negative x plus 1 is 0. Any one of those three things will make that first equation work. Well, nothing can happen here because e to any power is never 0. E to anything is a positive number. So I get y equals 0 or x is equal to 1 from that first equation. Similar stuff, although different in the end, will happen with the second equation. This becomes x equals 0, e to the negative x minus y equals 0, minus y plus 1 equals 0. Which means that x equals 0, this one's out, or y is equal to 1. But remember, I need both of those equations to work, which means I have to pick something out of this or this, and something out of this or this. So let's look and see how we can combine these. If I have to pick something from here and something from here, what can I do? Well, I can pick y equals 0. If I pick y equals 0, well then what could happen? I have to either have this be true or this true. But if y is 0, y can't equal 1, so the only other choice is x equals 0. And if I didn't pick y equals 0, then I had to pick x equals 1. But if x is 1, then x can't be 0, so y had better be 1. So I actually get 2 critical points out of this, 0, 0, and 1, 1. So let's look at the graph of this function and also confirm that I have 2 places which are maxes or mins.
And in this Mathematica notebook, I've plotted the function xy, e to the negative x minus y, over the range minus 2 to 4 for x and y. Again, I've labeled my axes, and I've told it the plot range, that's the z values that I'd like to see, are between minus 1 and 2. So we can definitely see a couple of funny things happen. Notice already in this view, notice what's happening up in here. You can sort of see these dark circles. These are actually, it's a byproduct of the way Mathematica graphs it. These are actually our level curves for what's going on. And what's suggesting is that something funny is happening right up in here, which is our point 1, 1. And we'll take a little bit more of a close look at that in just a few minutes. Notice that we've found algebraically 2 critical points, the point 0, 0 and the point 1, 1. This point 1, 1 is actually locally a maximum. It pops up right around 1, 1 and then comes down elsewhere. We'll zoom in there in a few minutes and look at that, but I'd also first like to look at the point 0, 0, our other critical point. 0, 0 is right where that really funny thing is happening. So this is actually what we're going to call a saddle point, right at 0, 0. If we look right around that point, it looks just like a horse's saddle. And what's happening is there really is a horizontal tangent plane, but it's actually not a max or a min, because if we look in the one direction, if we look at where my cursor is going now, it looks like a min, but if we move in the other direction, it looks like a max. All right, so overall, it's neither a min nor a max because it moves up in one way and down the other way, but it is nevertheless a critical point because it does have a horizontal tangent plane. And from that view we just had a second ago, we could start to see those circular type level curves. Can't find it again, but that's okay. All right, let me zoom in around the point 1, 1. So let's go from 0 to 2 for x. And 0 to 2 for y. Zooming around our other critical point and see if we can be sure that really that is a max also. It's a little tough to tell. It looks pretty flat. It looks sort of like a plane, but notice that if we look along the y-axis, it really is curling down at the edges on both sides. Right, so it's curling down clearly on the left and a little less clear on the right, but it is in fact curling down. And if we spin it around and look at the y direction, we see the same thing. It really is curling down in both the left and the right. And right around that point 1, 1, we saw those right there. We saw those circular level curves again, and the point 1, 1 really is a local maximum. So those 2 points are the only 2 critical points from that function. One was a saddle, and one was a local max. There are some good circular level curves.
All right, and last, we'll look at our second derivative test. To classify critical points as maxes or mins. Or possibly neither. Remember that in Calc 1 we may have had a critical point, which is an inflection point. So it was a point which had a derivative of 0, but it wasn't a max and it wasn't a min. So we're going to get something similar here. The process is a bit more complicated and the proof that it works is actually much more complicated. We're not even going to look at a real explanation of why it works. It's a bit much. I mean, it's actually a linear algebra type question. You've got to look at a matrix. Lots of Calc II stuff really is best described using matrices and linear algebra, but we're not going to worry about that for now. I'm just going to describe the procedure and we'll practice applying it. And so here's how it goes. We're going to use second derivatives. So we need to use, remember, if we have f sub x and we have f sub y, well then I can think about these as having, each of these as a second derivative as well. F sub x, f sub xy. Right, the derivative of f sub x with respect to x and the derivative of f sub x with respect to y. Well, f sub y also has f sub 2 derivatives. So we really have 4 second derivatives rather than just a single second derivative back in the Calc 1 case. And so what we're going to do is we're going to combine all 4 of these together into a single object, which we're going to call D again. A D is something that we're going to use to classify these maxes or mins. And so here's how it works. It's going to be f sub xx times f sub yy minus f sub xy squared. Now remember that f sub xy is the same thing as f sub yx. So really this is all 4. This is f sub xx, f sub yy, f sub xy, and f sub yx. All 4 are put together into a single quantity that we use to classify our critical points. And then here's the rule. Okay, so our classification scheme. If D is negative, then what we get is actually not a max or a min. We're going to look at it a little bit more closely, but it's our analog of an inflection point. It's a saddle point. So we'll look at examples of these, but really we call them saddle points because we think about, if I looked at the shape of a saddle, well then right here I have a horizontal tangent plane, but it's not a max or a min. And so that's what's happening if D is negative. I get something that essentially follows that shape. If D is positive, well then I need to do something else to decide whether or not it's a max or a min. If D is positive, then it's definitely a max or a min, and I just need to decide which one. So then what I'm going to do is I'm going to look at f sub xx. That's the second derivative, the concavity in the x slice, right? So in the x direction. So if the concavity, if it's concave up, remember, if it's concave up, that means it's a min. If it's concave down, then it's a max. We could have just as easily used f sub yy here. It will get us the same answer, but we only just, this is our procedure that we're going to write and stick with. Other things would work, but this is fine. And finally, if D equals 0, this is sort of like saying that the second derivative was 0 back in a Calc 1 case, and I can't make any conclusions about that. I have to do something else. I get no info out of that situation. So let's look at an example to apply that. Let's do one which we've already done much of the work for. Suppose that we have the function f of xy is xy e to the minus x minus y. We already discovered that the critical points are 0, 0, and 1, 1. And in fact, we already looked at the graph to see what should be happening, but let's apply that process just to make sure. So we actually already have f sub x. Let's just look at it again. F sub x, remember, was xy times e to the minus x minus y times minus 1 plus y times e to the minus x minus y. And f sub y was xy e to the minus x minus y minus 1 plus x e to the x minus x minus y. Which, let's actually simplify these. This is, I can actually factor out, again, let's factor out our y e to the minus x minus y. And then I get negative x plus 1, and f sub y is x e to the x minus y times minus y plus 1. So here's f sub x, here's f sub y. If we want to take our second derivative test, we need to actually know all 4 second derivatives. Or really just 3 of them because the 2 mixed ones are the same. So I need to take these and calculate the derivatives again. So f sub x, taking the derivative of this with respect to x. It's again a product because I've got something with x and I've got something with x. So I need to apply the product rule. First, times the derivative of the second with respect to x is negative 1 plus the second times the derivative of the first with respect to x. With respect to x, y is a constant, so it just goes along. E to the exponent times the derivative of the exponent. f sub xy. Start with f sub x, take the derivative with respect to y. Now when I take the derivative with respect to y, it's actually not a product because, well, between these pieces, it actually is a product. This is a constant. I need to actually now think about it as a product like this because I've got a y here and I've got a y here. So this is just a constant that goes along. Minus x plus 1 is the constant that will go along. And then I need to apply the product rule to these pieces. First, times the derivative of the second, which is e to the minus x minus y times minus 1, plus second, times the derivative of the first, which is just 1. And then finally, we need f sub y. Well, that's going to be very analogous to what we did with f sub xx. I need to take the derivative of this with respect to y. Now I have a product. I've got something with a y. I've got something with a y. So we take the first times the derivative of the second plus the second times the derivative of the first with respect to y. And this is what we get. And since these are pretty complicated, I'm going to go ahead and plug our points in. So remember we have the points 0, 0, and 1, 1 as our critical points. So let's just start with 0, 0 and see what we get. f sub xx at 0, 0 is 0 plus 0 because this is going to be 0. So I get 0. F sub yy at 0, 0 is again 0 and 0. F sub xy. Now when I plug in 0, 0, I'm not going to get 0 back. I'm actually going to get 1 times 0. That piece is all 0. When I plug 1, 1, when I plug 0, 0 in here, I get e to the 0, which is 1 times 1. So I get 1 times 1, which is 1. So f sub xy is 1. So d is fxx, fyy minus fxy squared is 0 minus 1 squared is negative 1, which tells me that 0, 0 is a saddle, which is what we saw when we looked at its graph on Mathematica. Let's keep all this up here and then look at our second critical point, 1, 1. that 1, 1, when we plug our point in, I get 1 times e to the minus 1 minus 1, which is e to the minus 2, times minus 1, plus. Now when I plug 1 in, this term all goes to 0. So that's negative e to the minus 2. That's the yy. When I plug 1, 1 in, this makes 1 times e to the minus 2 again, times minus 1. And the second term goes to 0. So I get minus e to the minus 2. That's of xy. This is 0, but I plug 1 in for x, so the whole thing is 0. So d is fxx, fyy, minus e to the minus 2, minus e to the minus 2, minus 0 squared, and that's positive e to the minus 4. But that e to the minus 4 doesn't mean it's a negative value, it's just 1 over e to the 4th, which is a positive number. So this is where we have to go into our second level. D is positive, so now I need to decide whether it's a max or a min by looking at just f sub xx. And f sub xx is negative, so D is positive, f sub xx is negative, so it's concave down, which means it's a max. Which is, again, what we saw on our Mathematica graph. And this is a good example because it was kind of complicated in between, but we saw a saddle point, and we saw the application of using that second level to determine whether it's actually a max or a min. And this is about good for section 12.7, 12.8, and next we'll move into 12.9. All right, and today we're going to look at our last section in chapter 12, Lagrange multipliers. And Lagrange is a mathematician that came up with this idea, and it's a clever idea to solve maximization and minimization problems of the following type. So we're going to solve max-min problems subject to a constraint. I'll draw a picture and show you what I mean by this. All right, so let's say that we got our favorite starting picture. We've got some function that makes some surface, and I only care about what happens. Suppose that this function is something like temperature, or temperature on the xy plane. So at any given point on the xy plane, this height tells me the temperature at that point. Suppose that I'm a bug that's just walking around on the xy plane on some curve. And I want to say, what is the maximum temperature if I stick to this curve that's in the xy plane? And in that case, well, then we have to pull this curve up to our function height way above and ask, well, what is the maximum height above the curve? And so now we're no longer looking for these places where the tangent plane is horizontal, because if I just follow this curve in the xy plane, the tangent plane may not be horizontal at any of those points. So we have to come up with a different strategy. And the idea of Lagrange multipliers goes like this. Right, so we're going to maximize the function f at xy, and we're going to maximize this function subject to a constraint in the xy plane. So the first picture that I drew was the xy plane was horizontal and our function value was vertical. But right now I just want to look at just the xy plane, and suppose that my constraint curve, this is my curve that's in the xy plane, that is my constraint. Well, if I have any curve then it's some formula involving x and y. Right? So maybe x squared plus y squared equals 9 is a circle of radius 3. But I could take that and I could bring everything to the left-hand side and get it equal to 0. And I can say that this constraint curve is g at xy equal to 0. So it's some algebraic expression. I have some equation in x and y. And if I put everything on the left-hand side, well, then I have some expression set equal to 0. And this is my constraint. And so we'll look at some real examples of that in just a little bit. But so we've got our constraint. And now we want to think about it like this. All right, suppose that I started putting some level curves of the function. All right, so here's a level curve. Now this function might have level curves that aren't circles, but that's okay. Here's a level curve. Here's a level curve. Now, if I looked at all sorts of level curves, and suppose that these level curves were getting bigger as I moved out. Right, so maybe this is level curve corresponding to height 1, 2, 3, 4, and so on. Right, so based on this, what can we say? Well, my constraint curve has a point where the function value is 4, so I certainly know that the maximum value along the constraint is at least 4. The question is, does it get bigger than 4? Well, yes, it does. I know that I have a value that's bigger than 4, well, because, say, over here, right over here, my constraint curve goes outside the level curve of 4. And if the function values are getting bigger as we move out, then right in here, I have a slightly larger z value. So the real idea with Lagrange multipliers is to say, well, what I'm looking for then is I'm looking to push my level curves just out as far as possible. Right? I want my level curves to be out as far as possible and no further. And if I want them to be no further, then really what I want is I want my level curves to be tangent to the constraint curve. Because in that case, the constraint curve doesn't go any further out beyond the level curve, so there's no greater function values. And so this is the key idea in Lagrange multipliers, to look for points where the level curve of the function is tangent to the constraint. Now, if it's tangent to the constraint, what does that really mean? Now we need to go back and think about the gradient vector. All right, so recall that grad f is perpendicular to level curves. So grad f is perpendicular to level curves. We can also look at grad g, the gradient of our constraint function g. So if grad f, if the level curves have to be tangent to the constraint curve. So I got my constraint curve, and I have this level curve here that's tangent right at that same place. That means that the gradient vector for each has got to point in the same direction, maybe opposite directions, but grad f and grad g have to be parallel. Because grad f points tangent to the level curve of f, and grad g points tangent to the level curve of g. And g equals 0 is a level curve of g. Right, so these are parallel, and what it means for vectors to be parallel is that grad f is some multiple of grad g. And so this is the Greek letter lambda, and we use it as our multiplier. We call it our Lagrange multiplier, because lambda for L for Lagrange. And so what we're really looking for when we talk about using Lagrange multipliers to find maximizations and minimizations of functions subject to a constraint is solving this equation here. So let's do that with a couple of examples. So let's maximize e to the 2xy subject to the constraint x cubed plus y cubed equals 16. Now this is a funny constraint. It's not a function that we've seen before. When we're done here doing the algebra, we'll look at some mathematical graphs and see how it works. But we'll be able to. This is just a curve in the xy plane. So the idea again is we're following this curve in the xy plane. We're looking for the point on that curve over which this has a maximum and minimum value. So let's maximize and minimize. All right, so G, our constraint curve, says take the curve as it's given, put everything on one side. So x cubed plus y cubed minus 16. And so what we've got is f at xy is e to the 2xy, and g is equal to 0. That's what we're looking for. So we need grad f. Grad f, if I take the derivative with respect to x, then we have e to the 2xy times the derivative of the exponent with respect to x, which is 2y. And we have e to the 2xy times 2x. Grad g, take the derivative of g with respect to x, and I get 3x squared, and I get 3y squared. Lagrange multipliers said grad f equal to lambda grad g. So what we need is grad f equals lambda grad g. So when is that going to happen? Well, that's only going to happen if each of these components match. So this is really just a shorthand notation for saying 2y e to the 2xy is lambda times 3x squared. That's the first, the x components, or the first I components. And the second, we need the j components. 2x e to the 2xy is equal to 3y squared times lambda. The other thing that also has to be true is that g has to equal 0, which is our original constraint. X cubed plus y cubed had better equal 16. Now this is 3 equations, and it's 3 unknowns, x, y, and lambda. Now the problem with this is they're not linear equations. If they were linear equations, well, we could do some linear algebra. It's a system of linear equations. You could solve for one variable, plug it in, solve for a variable, plug it in, and backtrack it. There's no set way to solve these. So we just have to look around. Sometimes we can be clever and things work out nicely. Sometimes we can solve for a single variable and plug it back into other things and everything is good. One general strategy might be to solve for lambda in one of these equations, plug it in down here, then we've just got equations with x and y between these two. But so we're just going to look at these and see if we can find anything that will reduce our number of equations. Okay, so what can we say? Let's just take this top equation. Let's do what I just suggested. Let's take this top equation and solve for lambda. If I solve for lambda, I get 2y e to the 2xy divided by 3x squared. If I plug it back into that second equation, it becomes 2x e to the 2xy is lambda, which is 2y e to the 2xy over 3x squared. That's lambda times 3y squared. That's my second equation. So already we can see some nice stuff is happening. Our 2x e to the 2xy is going to cancel out of both sides. And this then will simplify to 2x. Actually, let me bring the 3x squared up to the left. And I get 6x cubed is equal to 6y cubed. Well, that's great. That tells me that x cubed is y cubed. Now, if x cubed is y cubed, I can go to this last equation and say that x cubed is y cubed, so this becomes y cubed plus y cubed is 16, which says that 2y cubed is 16, which says that y cubed is 8, so y is 2. And if y is 2, then x is also 2. So now I have my x and my y that work. And there's a single point, 2, 2. We'd have to do we'd have to apply some other techniques. We're not going to worry about that for right now, but we would have to apply some other techniques to determine whether that's actually a maximum or a minimum. But for right now, we can be sure that this is the point at which the function attains either its maximum or minimum. We could just look at 2 points close by and see if it goes down or goes up on either side. But according to Lagrange multipliers, this is the solution. Let's look at another one. And so let's look at one final example. This one will be a function of 3 variables, and so the constraint is also in 3 variables. So now we've got a function on all of space, x, y, z, and our constraint is also something that's just in space. This is sort of like a sphere, x squared plus y squared plus z squared is a constant, but since these things are changed, they're not all the same, it's actually going to be more of an ellipse type. It's an ellipsoid. It's sort of an adjusted sphere. But we're going to do the same thing. G is going to still be a function of x, y, z, and we're going to get it by taking our constraint and putting everything on one side. And then we need to calculate grad f. If I take the derivative with respect to x, I get yz. If I take the derivative with respect to y, I get xz, and the derivative with respect to z is xy. Grad g is lambda times 2x. The derivative of this with respect to x, everything else is 0. Lambda times 4y, and lambda times negative 8z. Positive 8z, that's supposed to be positive. Or lambda, that'll be lambda g, not just grad g. Lambda grad g. If grad f has got to be lambda grad g, then these things must be equal. Which means that yz is lambda times 2x, xz is lambda times 4y, xy is lambda times 8z, and don't forget our original constraint, x squared plus 2y squared plus 4z squared is 9. So these are our 4 equations and 4 unknowns, and we need to solve them for all of the variables. All right. If nothing jumps out to start, we're just going to go through, solve for one of the variables and plug it into the others and see if anything falls out. So let's just take this top equation and let's solve for lambda. If I solve for lambda, it becomes lambda is equal to yz over 2x. If I plug that into the second, I get xz is equal to lambda, which is yz over 2x times 4y. The z's cancel, and this becomes 2x squared, if I bring the 2x up, is equal to 4y squared, which says that x squared is equal to 2y squared. Well, that's great. That's pretty nice for lots of reasons that we'll see in a little bit. In particular, we can look at this constraint equation and see that we can get this in terms of y, and we've got this in terms of y. So if we could somehow get z in terms of y, well, then we'd be in pretty good shape. So let's use our lambda and plug it into this equation as well. So if I plug in my lambda for this equation as well, actually, let's do this. Let's do something very similar. Let's start with this one. Let's solve for lambda, and then I get xz over 4y, and then I'm going to plug it in for lambda here. And so that this becomes x, y is lambda, which is xz over 4y, times 8z. And then we see what happens. The x's cancel, and I get 4y squared is 8z squared. which tells me that y squared is 2z squared. Which means that now I can take x squared and turn it into y. I can also take z squared and turn it into y. And so I can take this final equation and convert everything to y's. X squared is 2y squared. 2y squared is 2y squared. Well, 4z squared is 2 times 2z squared. So that's 2y squared. And that's got to equal 9. So I get 6y squared is 9. So y is plus or minus the square root of 9/6, which is plus or minus the square root of 3/2. If y is plus or minus the square root of 3/2, then I can come over here and say that x is the square root of 2y squared, plus or minus. So x is plus or minus the square root of 2 times this, which is of 2y squared, but y squared is 3/2, so I get plus or minus the square root of 3. And finally, we can come up here, so let's get rid of what we don't need anymore. So what we've discovered at this point is that y can be plus or minus the square root of 3/2, and using either of those versions, I get x is equal to plus or minus the square root of 3. Notice that already we actually have 4 points, because y could be plus or minus whatever, either this, and whichever I put in. If I put y equal to be the positive square root of 3/2, then I'd still get that x is plus or minus the square root of 3. So there's 4 different ways of combining these things together. And then finally, we're going to come over to this equation. If y squared is 2z squared, well, now I know what y is, so I know what y squared is. Y squared is 2z squared. Well, y squared is 3/2, and that's 2z squared. So that's 3/4 is z squared. So z is plus or minus the square root of 3/4. And again, it doesn't matter whether I have the plus version or the minus version. I still get 2 choices. So I get z is equal to plus or minus the square root of 3/4. So this is 2 choices, this is 2 choices, this is 2 choices. We actually get 8 x, y, z combinations. So we've got x, which is positive root 3. Y, we've got a positive for everything. So that'll be positive, positive, positive. We can make positive, positive, negative. We can make positive, negative, positive. We can make positive, negative, negative. And then we can do all of these same things with the negative for the first component. So negative root 3, positive, positive, negative, positive, negative, 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 positive, and negative, negative, negative. So these are 8 different possibilities for the max and min of the original function subject to the constraint. And so finally, we need to take all of these and evaluate the function at those points. And whichever one gets me the biggest function value, well, that's the max subject to the constraint. Whichever gives the lowest function value, that's the min subject to the constraint. So let's evaluate our function. Remember, our function was really just x, y, z. So we just need to take the product of all of these. And they're all just plus or minus, so we're actually in pretty good shape. We can say that the max is going to be at any point which gets me a positive version of it, and the min is going to be any point which gets me the negative version of it. Right, so the max value is at the product of all of these, root 3 times root 3 halves times root 3 fourths. And that occurs a bunch of different ones. That occurs anytime we have, so this is a max, because I have two negatives which will cancel out. This is a max. And this one is going to be a negative version, so that'll be the min. That'll be a min. This will be a max, min, min, max. It's a complicated problem, but some of them are complicated, and it's good to work through some of the simpler ones as well as some of the more complicated ones. But that's the basics of Lagrange multipliers. In fact, that's everything we need to say about 12.9. And at this point, we've finished halfway through the semester. 2 more chapters to go, 13 and 14. So I'll see you for those next time.